Good day, everyone. So let us continue our discussion, and today we'll talk about problem solving in or problem solving agent in AI. Here's what you'll find in this lecture. First one, what is a problem solving agent? What is problem solving? And its examples. So let's first recall what an agent is based on our previous lecture. Um, an agent is anything that can perceive its environment through sensors and affects its environment using actuator. We'd also looked into various properties of environment, but for now, we'll just focus on environments that are fully observable, discrete, and deterministic. So note that our agent's primary goal is to achieve the best outcome, or if not possible, the best expected outcome. So those definitions in mind does not describe what a problem-solving agent is. So basically, a problem-solving agent is a type of rational agent where its primary goal is to solve a given problem. So it does so by examining possible future actions, learning ahead in order to solve the given problem. But before we go any further, let's first understand what problem solving agent or what is problem solving. Okay, so some important definitions. So problem solving is the process of finding solutions to various issues or problem. And a problem in this regard is defined as an inquiry given various conditions with intent to get to the facts. Okay, so one example of problem-solving domain, which is quite sort of extensively in the field of computer studies, is called search problems. So in order to create problem-solving agent that can solve search problems, we have to first formally define a problem. Okay, so in AI, a problem is defined using the following components: the initial state, this first one here, the initial state of the problem, successor function, goal test, and finally the path cost. So such that a solution is a sequence of action transforming the environment from a given state to a final goal state. Okay, so let's use this picture. Say for example, this picture. So we have this problem. We'd like to find the shortest route going to J from A. So here's the location of A, and here's the location of J. Okay, so provided the conditions, we have the map, the cost of moving from one place to another in the agent. Okay, so now let's define the components in the search problem. And then the initial state of the problem is defined by the agent state plus environment conditions prior to finding the solution. For the routing problem, this includes the position of the player, the condition of the location, whether visited or not, and the condition of the status or the status of the nodes, whether it is visited or not, and or you're already in the goal state or not. Okay, so let's say that S sub 0 is the start state in A, where you find the current location of the agent. Okay, so the initial state here is the agent state, environment state at the beginning of the problem. So that's the first position of your agent in AI. So let's say your agent is currently at A. So you have to find the route from A to J where S sub 0 is in A. So you're here, okay, currently. So next we define the successor function. So this function takes an input, a state, input as a state, and it returns us an output the list of all possible permissible action and its corresponding change in the state such that given S, it returns an A sub 1, S sub 1 pairs. So action takes pair. Okay, so it's always a pair. Okay, so the action and then the ending state. Action, the ending state. All right, so let's move on. Say for example, we want to go to B. So you're right here. So after that, we're now in B. Or for example, you're from A, go to F. Okay, so as stated here at the top, go to F, now you're in F state. Okay, so far so good. Okay, so let's look back at our example. So S sub 0 in A, and then we give it a parameter to successor function. So the parameter um, of successor f of n is in the state in A. So this function will return the list go B in B, go F in F. So that's your action state. Okay. So before we proceed to the third component of the problem, let's take a look first at what is called the state space graph. So for us to better understand the successor function. So this is an example of a state space graph. So we see how states are related and how the agent traverses the states. So at each point of the exploration, okay, uh, so at each point of the exploration, the state can be divided into three parts. We have the blue states marking scored region of the graph. So these are the visited nodes or states. Okay, and then marking the frontier, meaning the possible immediate next states to be explored. And the red states, or it's more like a peach-colored states, marking the unexplored regions of the graph. So the blue ones are the nodes, or let's say states that are already visited by by our agent. Okay, the black ones are the next state to be visited by our agent, and then the red ones or peach colored states or regions are the ones that are unexplored yet. Okay, so they are divided into three. So for example, we're already in E, and in every exploration we make sure that we check whether we have reached the goal state using in E. So now we are here in the goal test. So with that, we can now proceed to the third component. So the goal test is like the successor function. The goal test is also a function, and what it really basically does is that given a state, it will determine whether or not the agent has reached the goal, which is J in our example. So we make sure that every exploration, every stop in each region, we have to check whether we have reached the goal state. Okay. So since the goal of the agent is to reach the state J, uh, based from our graph, so we want to reach J, and we are currently at state E or region E. So it's not yet the goal state. Okay. So goal test in E, for example, we are in E, so it would return false. Okay. And then last one, or lastly, we will determine the path cost, like the successor function, the goal test, and goal test. Path cost is also a function. It receives an input, sequences of state, action, transition, returning the cost of that sequence. So this is very useful if we want our agent to return the best solution. Okay, so we're computing to the path cost. So this path cost here could represent the distance between each node from one node to another, or the time it takes to travel from one node to another. So you could see this graph. You could imagine this graph as a roads, and then the states are the cities. Okay, so they are labeled with the distance, or let's say the time that it takes to get from one place to another. Say for example, we want to know the cost from A. So this is A here to G. So A to G. Okay, so giving that as a parameter to path cost, it will return the value 24. So if you're going to take the route A to F, so that's 15. The path cost is 15 plus 9 from F to G. So 15 plus 9 is 24. Okay, so if you're going to get or to use another route, say for example A, B, E, F, G, so that would cost more than the first one. Okay, So now let's move, or let's have more visual examples. Let's look at a vacuum agent. So first we have to define the components of a vacuum cleaner agent problem. Okay. So now for our initial state, any configuration of the environment can be in this agent in column A or B. So where A or B is either clean or dirty. Okay. So successor functions can be any legal state. So it can be clean, unclean, resulting from any of the possible actions of the agent, left, right, or suck dirt. Our goal test is, are all the cells clean? Okay? And the path cause is given a sequence of agent action, how many steps has been done by the agent. Okay, so that's a glimpse on how to create a problem-solving agent. So more on the actual algorithm for making the agent function or the agent solution under them in the coming lectures. So that's it. Thank you for watching.